First one is that SO3 is a non-abelian group. Okay. So this is easy to verify mathematically, but physically what we're saying is that rotations in 3 dimensions don't commute. Okay, so you should be familiar with this fact, but let me just give you a very brief, demonstration of what I mean. So, take the rotation sequence where you first apply rotation on an object around the x-axis. So this is rotation around the object on x-axis, and then you rotate the same object by 90 degrees around the y-axis. So, let's take a book, okay? So suppose we have a physics textbook, and this is the y-axis, this is the x, and say this is a z-axis, and first, we are going to do a rotation, suppose in that direction by 90 degrees. So if I do this, then the book goes to this configuration. And then let's do a rotation around the y-axis by 90 degrees. So if I do that, then the book, sorry. Goes to this configuration. Do you agree that if I rotate it around the x-axis, then the book goes to this, and then if I rotate it around y, then it goes to this configuration, right? So what if we started, but now let's look at a different rotation sequence. So let's call it rotation sequence 2, where first I do the rotation around the y-axis by 90 degrees, and then rotation around the x-axis by 90 degrees. Okay? So if I start with the same configuration as before, sorry. Okay, so I'm just lazy. So now we are rotating in this direction around the y-axis by 90 degrees. So if I do this, then I still get the P. I can still see the P. And then do a rotation, the same rotation as before we did above, but around the x-axis. And if I do this, then the book goes to that configuration. Okay, so if I compare, so this is this guy with this guy, we see that even though in both cases we started with the same configuration, we ended up at a different configuration because the two rotations don't commute, right? Is that clear? Okay, so I mean, you can do the same thing, but if, for example, if you say, okay, I'm going to take the, theta 1 equals to 90 degrees, and then theta 2 equals to 90 degrees rotation, and compose them, and that is not going to be this composition, right? So that's basically mathematically you can show that, right? And the fact that, so this is related to the fact that the Lie algebra is a non-commutative Lie algebra, right? That the generators do not commute, that this is, the right-hand side is not zero. It's a consequence of this fact. Okay, I just wanted to relate the mathematical fact with the physical fact, which is more familiar and very easy to verify. Okay, any questions? Okay, so next comment. Actually, let me write that down, okay. This is a consequence of the fact that the generators of SO3 do not commute. All right. All right, now next comment is so the rotations in 3D involve rotations in 3 independent uh, 2D planes. Okay, and this is actually a theorem that you can show that any rotation in 3D can be made out of 3 rotations. And what are these planes? For us, it's x1. Well, we are using 1, 2. So the 1, 2 plane or the xy plane. So we are going to switch between these 2 notations, or the 2, 3 plane, or the yz plane, or the 3, 1 plane, or the, say, zx plane, right? And what happens is that the Levi-Civita symbol, epsilon ijk, maps 1, between a plane, a 2D plane, including its orientation, right, to the unit vectors, ijk. Okay, and vice versa. So if I so this is basically related to the fact that in 3 dimensions, we can specify rotation by either rotation around an axis or by specifying what plane the rotation is in, right? Now, would you be able to do that in, say, if you were in a 4-dimensional space, would you be able to specify rotation in terms of rotation around an axis?
Would it be 4 axes? That's what I thought.
Right. So let's see. Suppose we are in 4 dimensions, right? So we are in 4 dimensions, and this is the XY plane. Now, there's going to be a Z plane, which is at 90 degrees, but there's also going to be a W plane, which is also at 90 degrees, right? So there's an ambiguity when it comes to choosing a unique direction, a unique axis perpendicular to X and Y plane, right?
Oh, so there would be a plane that's perpendicular to this plane.
Exactly, the WZ plane, right? So that plane, so in higher dimension or in dimensions other than 3, you have to specify rotations by specifying the plane. And this is related to the fact that the epsilon ijk, the Levi-Civita symbol, is a 3-dimensional object, right? And it maps 2 dimensions to 1 dimension and vice versa. 2 directions to 1 direction. It only works in 3 dimensions, right? Okay. So this is a 3-dimensional object. So this, the cross product is a product you can only have in 3 dimensions. And therefore, when you are working in higher dimensional objects, which you do always in mathematics all the time, you don't use cross product, but there is a, analog in higher dimension. Is called so this is a side note, a wedge product. Okay, so this is denoted by, and it's related to differential forms and stuff like that. All right, so but we won't go there. So let's look at this rotation. So in the XY plane, typical rotation is going to look like, let me switch, R is more of a natural symbol for thinking of rotation. So the rotation around the Z-axis, say by an angle, let's, so this is going to be the rotation in the XY plane, right? Because it's going to be the rotation of the Z-axis. So the matrix will look like cosine of theta 3 minus of sine theta 3, sine of theta 3, cosine of theta 3, 0, 0, 1, 0, 0. Okay. Are you familiar with this at all? Are there anyone who is not familiar with this? No, it cannot be both, right?
I've seen it before.
Okay, good. Yeah. So, and again, something you can verify for yourself that, this is actually given by e to the power, say, theta 3x3. Okay. The x3 that I gave above is going to, if you now write the right hand side, sorry, it should be, if you expand it as a formal power series, Okay, so these are fun. These are fun exercises. At some point in life, you always have to do these things. Oh, what am I doing? Too many indices and too many powers and stuff like that. Yeah. Okay. All right. So this is a nice little exercise you can do for yourself, but this is, I mean, are you convinced of what is it doing? It's basically what it's doing is that it's not acting on a vector, a three-dimensional vector on the z-axis, but it's acting on the x and y component. And it's acting in a way such that the length of the vector remains invariant. So let's verify that. So let's take a vector r. So we have x and y and z. And so r prime is going to be, say, r around z angle theta 3. Then this is cosine of theta 3 minus of sine of theta 3, sine of theta 3, cosine of theta 3, 0, 0, 1, 0, 0, acting on x and y and z. So what happens is that the x component and the y component get mixed up, right? So it's x, it becomes x of cosine of theta 3 minus y of sine of theta 3. And the second component becomes x of sine of theta 3 plus y of cosine of theta 3. And the z component, nothing happens to it. Okay, so this is r prime. Now, if I look at r prime, transpose r prime, then I get the first term is x cosine 3 minus y sine 3 whole squared plus x sine 3 plus y cosine 3 whole squared plus z squared, right? Now, if I expand it, I get x squared cosine squared theta 3 plus y squared sine squared theta 3 minus 2x1 xy sine theta 3 cosine of theta 3. And similarly here we get x squared, but instead of cosine, I get sine here. And here the sign flips, but I get the same thing, sine and cosine. And then I have z squared, so we get these guys canceling out. And by our favorite Pythagoras theorem, which is sine squared plus cosine squared is 1, is, sorry, not this one and this one, right? Yeah, we get x squared, and this one, we get y squared and z squared, which is r squared, okay? So we have verified that this guy does actually, and you can even okay, you can do geometry now, right? So you say I start with a vector r, position vector r, and I rotate it. So I don't want to, so I rotate it by some angle, theta, and so this new vector is r prime. Now you can verify that this is actually r, that if r is given by x, y, and z, that r prime is given by this, okay? Just by doing some elementary geometry. Okay, so that was the form of rz, but then we can write similarly, say our rotation around the x-axis. So the rotations around the x-axis will have this form. The minus sign here. The minus sign is kind of, doesn't matter if it's there or here because sine is an odd function. And the fact that it's an odd function, you know, if you take theta to minus theta, you get the inverse element. So that's our x, and then similarly, our y is going to have cosine of theta 2, 0, sine of theta 2, 0, 1, 0, minus sine of theta 2, 0, cosine of theta 2. All right? So each of these, Rx, Ry, and Rz, they actually are elements of a subgroup. That's our next comment.